All right. Okay. They are. Yeah. All right. So if we had this would be like log base e of 0 would equal x. And if we needed to solve that, we could rewrite it as exponential e to the x equals 0. And what number could we put here that could possibly give us 0? If we put 1, that'd be e to the first power, which should just be e, which is like 2.74, whatever e is. E to the 0 is 1. Even if I put a negative number, like e to the negative 5, that's 1 over e to the 5th, which is not 0, right? It's starting to get close to 0, but it's not actually 0. So this is not possible. So natural log of 0 is undefined. Okay, and the same would be true here if we tried to put a negative number there. Whenever we take the natural log of a number, it must be positive. Okay. Now, if we take the natural log of 1, let's sort of think of the same thing with natural log of 1. So natural log of 1, let's say that equals some number we don't know. Let's call it x. Because this is one you'll use a lot and you need to have memorized, but sometimes students are less familiar with logs and they have a hard time remembering this. So this is like log base e of 1 equals x, which means e to the x power would equal 1 when we rewrite it. So what number would we put here to get 1? 0. So if x equals 0, e to the 0 power equals 1. So natural log of 1 is 0. Okay, so that's one that's important that you need to make sure you have memorized there. Natural log of 1 equals 0. And because natural log of 1 equals 0, that x-intercept on the natural log is going to be at 1, 0. Now, knowing what the natural log graph looks like is important mostly for our limits that we're going to look at. Because when we have to do limits of natural logs, we are going to need to know what that graph looks like because there's not really an algebraic way to solve them. So, let's look at some examples. Well, hold on. We're not doing limits yet. Let's do this. So if we look at this graph, we've got negative natural log of x plus 2. So normally, natural log of x plus 2 looks like this. It passes through this point right here at 1. But this is just natural log of x. So whenever we have two things that have happened to this graph right here. We have this negative and we have this plus 2. So what, Joe, does the negative do to the graph? Okay, so this is a flip over the x-axis. And it will also move this to the left, too. Okay, so if we flip this, let's flip it first. If we flip this graph, that would look like this blue line here. So that is negative natural log of x that we just graphed there in blue. And then we need to move this to the left too. So where normally we have this vertical asymptote right here on the y-axis, we would move that over 1, 2. Extend this out a little bit. So 1, 2, that's our new vertical asymptote. And we just slide everything over where this point right here was at 1, 0. We'll move that 2 points over, so that would be here. And then we would have a graph that looks like this. So this would be y equals negative natural log of x plus 2. Right, 1, 0, yes. And it has a vertical asymptote at the y-axis. Okay, so you're just using those transformations there. Now, let's think about the domain of this problem. Okay, so if I just look at the graph, what I can kind of tell from the graph, what are my x values for this problem? They're greater than negative 2, and I should have a negative right there. So domain, just looking from the graph, is x is greater than negative 2, right? Anything to the right of negative 2. It does not include negative 2 because that is a vertical asymptote. That line right there gets closer and closer and closer to the vertical asymptote, but it never actually touches it. Okay. Let's say that we didn't want to graph if we're asked about domain, but it doesn't tell us that we have to graph. We know that when we take natural log, whatever we're taking the natural log of must be positive. So what we can do if we're doing this without a graph is say x plus 2, because that's what you're taking the natural log of in this case, must be greater than 0. And then just solve that. X is greater than negative 2. Okay, questions? All right. I think I'm going to skip that second example there so we can move on. All right, so let's look at some limits. Now, don't get too caught up in these and forget the most easy way to solve a limit. And what is that? Plug it in. So, for this first problem, I've got the limit as x approaches 3 of the natural log of the square root of x squared minus 5 over x. So, I'm going to try just plugging this in. So, I'll have natural log of the square root of 3 squared minus 5 all over 3. Which is going to give me natural log of 9 minus 5, so I got square root of 4 over 3, which is going to give me natural log of 2 over 3. And other than typing it into your calculator and getting a decimal, you really can't do anything past that. So you would just leave your answer, natural log of 2 over 3, which I don't like, but is what these problems end up like most of the time. Okay, so direct substitution, pretty straightforward. Let's look, of course, most of them are not going to be direct substitution. Let's see. Okay. So copy these next couple down. Let me try to get rid of the answer on this one. Alright, so for these two examples, whenever we plug in 2 here, the natural log of 2 minus 2 is the natural log of 0, which is undefined, which tells us that the limit does not exist. But most of the time they're looking for something more specific than does not exist, especially when they give you a one-sided limit here. So if does not exist as the answer choice, choose it. But probably you're going to have positive infinity or negative infinity. So the best thing to do for these problems is to think of what the graph looks like. Okay, so if we think of our graph here, the original natural log just looks like this. Goes through 1, right? We're just going to move that over 2 so that that vertical asymptote right here, that is just going to be moved over to 2. And then this point right here that it passes through, it'll be moved over here. And we'll have a graph that looks like this. So, as we look at this, as the limit, as x approaches 2 from the right, what value are we going to get? Negative infinity, because we're looking at y values. So as y values are getting lower and lower and lower and lower and lower. The limit as x approaches 2 from the right of natural log of x minus 2 equals negative infinity. We already know it's going to be positive or negative infinity because the limit does not exist. So it's not going to be a number answer there because that would be a limit where we could plug in and get the answer. So let's look at 4 here. If we plug in 0, we've got natural log of 0, which is undefined, tells us it does not exist. So let's think of the graph here. So let's just draw that same graph we've been using that we start with. This is just natural log of x. Looks like this. This point right here is 1. What does the negative on the outside do? It flips it over the x-axis. What about on the inside? The y-axis. So what we have here is we have a reflection over the x-axis and a reflection over the y-axis. So if we do that, here's our reflection over the x-axis. And then we need to take that and flip it over the y-axis. So go through this point, -1 right here. So this red graph is our graph here. And as we look, as x approaches 0 from the left, what do we see happens to our y values? Okay? Positively infinite. So positive infinity there. Okay? So use your graphs on those. Okay, questions? Alright, so, okay, I'm going to let you copy down these properties of logs. Alright, so let's do a few problems with expanding. So we're starting with a single natural log, and we want to make the problem bigger. If we look at the first one, it's pretty straightforward. So if I've got two things that are divided, then I can break that up into natural log of x minus natural log of 5. All right, and separate those out. Okay, so these two are equivalent to each other. If I have number 6, I could do natural log of 3x minus natural log of 4. But is there anything else I can break apart there? Right, so we could have natural log of 3 plus natural log of x minus natural log of 4. There. So we could break the 3 and the x apart as well. And you'll see whenever we start doing derivatives of these things, that's going to be very useful. Because it's going to be easier to take the derivative of that whenever it's separated out versus whenever it's all together. Now, 7. 7 is really bad. So I would probably start with the division. So you've got natural log of x plus 5 squared minus natural log of x squared times the square root of x minus 1. Okay. What can we do with the exponents out front? So we will have 2 natural log of x plus 5 here. Can I break down the x plus 5 part? I cannot. There's no rule up here for things that are added together in the parentheses. You can't break that down. A lot of times kids get that a little bit backwards. But you're just going to leave this right here. But over here, I've got more that I can do. Okay. So I'm going to put minus, and then I'm going to put me a bracket right here because I'm subtracting whatever comes after this whenever I break up here. So I have x squared times the square root of x minus 1. So I can write this as natural log of x squared plus natural log of square root of x minus 1. Okay, anything further I can do? Good, so I have 2 natural log of x plus 5. And I think I'll go ahead and distribute that negative there. So I have minus 2 natural log of x. What about over here? Can I do anything there? Right. So this is the same as natural log of x minus 1 to the 1/2 power. So we can pull that 1/2 out front, natural log of x minus 1. And I distributed that negative there, so we have that negative. And I believe that's as far as you can go on that one. Okay, questions? Alright, so that's working on expanding. It can, at times, also be helpful to rewrite these as one logarithm. Not so much for derivatives, but if you're solving a logarithmic equation, it can be helpful. So for example 8, we've got natural log of 3 plus 2 natural log of x minus natural log of 5. What should we do first? I would combine the pluses, but what do I do with this 2 right here? Let's make that an exponent first. So that's going to be our x squared. I'm going to show every step here just because this is notes, and you might need to look back at it to see these. But then some of you may skip straight to this natural log of 3x squared minus natural log of 5. And then what's the last thing we would do here? Right. So natural log of 3x squared over 5. Pretty much you need to deal with those exponents first before you start trying to put anything together there. Alright, here is our next example. We're just about done with notes. Now, this 1/2 out front, it goes with everything. So I really need to get all of these things inside of the brackets put together before I can deal with that 1/2. I guess I could distribute it, but it's going to be easier if we just leave the 1/2 alone for right now. And then we're going to put that back into our natural log at the end. So the first thing I've got to do is that 3 has got to be an exponent here. And I guess while I'm at it, I could go ahead and put these two right here together since they are addition. Alright, so I'll have 1/2 natural log of, I'm going to write the x first, x times x squared plus 2 minus natural log of x plus 4 to the 3rd power. Alright, here. Okay, we've got subtraction, which means division, so I'm going to have 1/2 natural log of x times x squared plus 2 over x plus 4 to the 3rd. You can distribute that x if you want, but you don't have to. Then I got to deal with the 1/2. What's that going to look like? Okay, all of this stuff right here is going to be to the 1/2 power, which means that it's going to be it's going to be a square root. So I'm going to have natural log of the square root of x times x squared plus 2 over x plus 4 to the 3rd power. Okay, questions? Alright, I do need to show you just one more thing that I did not add on these notes. I'm going to add an example 10. And everything I've shown you here is the same if you have a like a log base 2 or a log base 7. You combine everything the same. We use natural logs for everything, except for your bases have to match. So you can't combine a log base 2 with a log base 9. They'd have to both be log base 2s. So let's say that we have log base 5 of x plus 3 equals 8. Okay, and these numbers may end up being awful. Yeah, it's going to be pretty big. But how do I solve this? Rewrite it as an exponential. So I will have 5 to the 8th power equals x plus 3. And we're going to use our calculator on that because I do not know 5 to the 8th power off the top of my head. Anybody got theirs handy? 5 to the 8th power. What do we get there, Tanner? Is that right? 390. Okay, and then we would just subtract that 3. So we'd get 390,622 as our x. Okay. Alright, let's try one like this. 4 natural log of x squared minus 3 equals 0. Okay, so what do we need to do here first? Move the 3. So we'll have 4 natural log of x squared equals 3. Then we need to divide off that 4 before we do anything else. So we have natural log of x squared equals 3/4. Hello? base for a natural log? E. So we've got e to the 3/4 equals x squared. And let's say we're trying to do this without a calculator. How do I get rid of a square? Square root. And square root is the same as to the 1/2 power. Right? So this would be e to the 3/8 power if they wanted you to do this without a square root, without a calculator. Or if you type that into the calculator, Tanner, what do we get? Let's see. Can't remember where it is at either. And you gotta hit the green button. So we get 1.45499. The other way you can think about this also, if we go back to this step, natural log of x squared equals 3/4. If you think of raising both sides to a power of e, e and natural log are inverses. They cancel each other out, so you get x squared equals e to the 3/4, which is the same thing we did over here. It's just a different way of thinking about solving the problem. We're raising both sides to the powers of e. Okay, so your assignment is going to be...
What is the number that we need to solve for exponential?
52. Alright. Alright. Your homework is going... Let me just go ahead and stop